So, good morning, everyone. My name is Prashant, and I'm working as a postdoctoral researcher in NRED. And today I'm going to present my one of the project which I am working right now in NRED. So, the title of my presentation is how you can optimize or optimize technology selection for microgrid integration for the island or the remote communities. So we made a multi-decision criteria based framework, and we done it for the three different places. One is for the Cordova, Alaska, another one is for the Makah tribe in Washington, and the third one is Molokai in Hawaii. So the outline includes the introduction, then we go through the method we adopted for the MCDM framework, and look for the three different case studies. First one is for the Cordova, Alaska, another one is for the Makah tribe in Washington, and the fifth one is for Molokai, which is in Hawaii, and last one we will go through the conclusion we will get from the MCDM framework. So let's begin with the introduction. So isolated or the remote communities are those which are pretty far from the mainland, or which is maybe pretty far or remote from the main grid of the nation. So the reliable energy supply to these communities are pretty difficult. So, and these remote communities having a small or isolated grid, as they are pretty far from the main grid system of the entire nation. So the resilience they required for their grid system, which is pretty small, and the energy storage and the energy supply is pretty difficult for them. So the problem is here how you can identify and integrated a suitable technology for the energy conversion, because we have a multiple technologies. We have multiple technologies, right? Whether it's the renewable energy sources or the non-renewable energy sources, but how you can define it for that remote communities. So for that, we develop our own multi-criteria based framework, which can help us to identify which particular technology is going to be suitable for that particular remote location. So we consider the reliability, efficiency, cost effectiveness, but how we have integrated it. We consider the technological performance of all the technologies we have right now, whether it's renewable or non-renewable. The other one is environmental impact, because as we are moving toward the carbon neutral economy, or we are moving toward where we have the zero carbon emission. So we consider the environment impact in our framework as well. We also consider the economic feasibility, and also we have considered that particular community need as well. So in this framework, we have considered the multiple technologies, which include the solar PV farm, concentrated solar power, hydropower, coal, natural gas, biomass, nuclear, wind turbine, land-based, or whether it's offshore, and also the marine hydrokinetics. So we have considered the three different remote communities. First one is the Cordova, Alaska. Another one is Makah tribe in Washington, and the third one is the Molokai, Hawaii. And so how this framework works and which method we have adopted, we consider average sum model, or also the weighted sum model and weighted product model to develop our own MCDM decision based framework, which align with the community's long-term goal. It also include the energy resource potential, the commercial viability, safety, cost effectiveness, environmental impact, and the efficiency. So first task for this framework is you have to identify the community. Then it will you have to define what's the main objective of your what you want to be there in the particular remote community. Then it done the initial technology screening by itself, depending upon your priority given to each objective. Then it will develop its own weighted objective tree, where you need to provide the weightage to a particular objective which you have defined in the framework. And then it will compare all the technologies all together depending upon the objectives you have defined for the remote communities. So the first method in this, how you can define the remote community. So for that, there is a project run by the Department of Energy, which is the Energy Transition Initiative Partnership Project, in which the 8 total remote communities has been applied, because these communities are want to be switched from their conventional source, which they are using right now, is a diesel generators. So they want to shift from the diesel generator toward the um, much more conventional, or you can say renewable based energy system, so that they don't have to rely on the non renewable energy sources because of their remote locations. So once you define the community, then you have to define the basic objective for that particular community. So our main goal is to provide the technology, right? That's our main goal. But here you can see the branches represents the benefit if you are apply that particular technology to that remote location, and the roots represents over here is how it's going to be benefited to that particular community for a long term, whether it's that technology should be efficient, reliable, safe, and scalable, and also the cost effective. So then the initial screening will be based upon all these factors, which include maybe the efficiency, levelized cost of electricity, and the capacity factors. This framework compare all these factors all together, and once it screen all the technologies, but you have to define how you need to then you have to define the sub objective of that particular technology, right? So this one is a it's kind of level one. Level one is a kind of you have to define a technology for a particular location. Then you have to define its sub-objective, how you can um, kind of how you can if you have to apply that technology to a remote location, how you can be there. So then the level one is the level one is so the level one is this one. Then the level two is it should be highly efficient, safe, levelized cost of it have a minimum levelized cost of electricity, reliable and scalable. But again, you have to go to particularly define the sub-objective in all of these, which include all of these factors. Depending upon under high efficiency, you have to define all these factors. Then in safety, what you have to be considered in the safety parameters, what you have to be considered in LCOE, and what you have to consider in reliability, and what you have to be considered in scalability. And considering all of these, then you have to define all of these. So level one is again, you have to select the technology, but in level two, you have to divide it in a depending upon the weightage, and that weightage gonna consider the community needs, then how you gonna be there. And again, level three, it's a sub objective of the level two. So it's a kind of how you can reach up to that technology by dividing the various objectives, so that when you fulfill one of these, or when you're going to fulfill all of these, then you will reach up to the level two. And when level two is completed, then you will pretty close to the level one. So that's how it works. So if we look for the case study for the Cordova, Alaska, so in Cordova, Alaska, there are 2,700 of residents, and in this particular remote community, the 60% of their energies come from the creek hydro power plant, and the 40% is again come from the diesel power plant. They are diesel generator they are using over that particular remote community. And for the Cordova, Alaska, they have mainly fishing and the tourism industry, but this particular region has a pretty high seasonal fluctuation in the electricity generation, because in summer you have to store your food, so it again required a lot of energy. And in the winters, when you have a snowfall over there, and the water freeze at that time, and heating also required a lot of energy. So because of that, this particular city has a lot of energy fluctuations. So if you have to select a particular technology for this particular region or for this particular community, depending upon by defining all the objectives and sub-objectives, this framework automatically reject most of the technologies, and then it will select only the four. And these are some of the calculations. But yeah, my goal is to represent. I have defined multiple objectives over here under the main four or five sub-objectives. And then you will see the kind of calculations. But yeah, I want to show over here is this algorithm or the framework provided four different technologies out of 12. And here MCATCH is a marine hydrokinetics open hydro, which fulfill around 83.4% of the community needs, whether it's a point of community needs, technology selection. It includes all of these objectives, and 83% of these objectives being fulfilled by this particular technology. And offshore wind is fulfill all the community needs and demands around 75%, and the land-based around again 75.6%, and the solar PV is around 70%. So when you compare all of these results with respect to the first preference given by the framework, so here you can see how it will fulfill all of these major objective of our the technology. So this framework provided the first preference will be given to the marine hydrokinetics, and another second preference for the offshore wind. The third one is for the land-based wind, and the fourth one is for the solar PV. And then if we look for the other case study, which we have performed on Makka tribe, which is in Washington, there are around 1,500 residents over there. And the main power supply is from the transmission line. But again, the backup power for that community is by the diesel generator. But because of the tsunami and the earthquakes, this region sometimes will be isolated for more than 1 year if we have a kind of huge tsunami at that point of US at that location. And even there are a lot of studies have been performed since 2002 to this particular region to look for what kind of technology you can implement that particular region. But at the time, it's not feasible as per this study in 2002. And again, they have tried to put aqua buoys over there to determine how much we can generate the power using the wave or tidal energy. And there is another project still going on in onwards from 2022, which still investigating the total potential of the wave and tidal energy over there. So we implementing all the communities need and on all of these technology. And again, it rejected most of them because of the different conditions over there on that particular region. And it suggested again the marine hydrokinetics is the best suitable for that particular location. And the solar PV is the second preference as per our framework. And the third one is for land wind, and the fourth one is offshore wind. The same, and one thing I want to share over here is this framework is well aligned with the study performed by the Pacific Northwest National Laboratory Lab. And then we done the same analysis for the another remote community, which is Molokai in Hawaii. It's been pretty far from the US, and it's totally remote because it's pretty far from the mainland of US. So and there are around 7,400 residents over there, and the 7% of the entire population of this remote area still is completely off grid. And there is a one town over there, we call it, the name of that town is Molakakai. And in this particular city, there is around 3,000 of residents. And apart from these 3,000 residents, there is still, we don't have the energy access to the remaining population over there. And for this particular remote island, 85% of their power is coming from the diesel generator, and only 50%, and the remaining 50% is come from the solar PV rooftops. So we done the same. We apply all these objective for that particular community. We define the power requirement, and so most of the technology been rejected, whether it's because each of technology has their own pros and cons. So it's been filtered the most of them, and we have only four. And as per our framework, the solar PV is the best suitable for that particular remote community. And the second one is for the land base wind turbines. Then the marine hydrokinetics is the third preference for that particular remote community, and the fourth one is the offshore wind. So the conclusion is for the three different locations which we have done the case study, the three different locations have the three first preferences are all is different. So for the Cordova, Alaska, the marine hydrokinetics is the first preference, whereas for the Washington, it's also the marine hydrokinetics. But for the Molokai, which is in Hawaii, the solar PV is the first preference for that. And the good thing is when we implement, if we're supposed to implement all these technologies in all these remote areas, you will reduce the diesel fuel consumption by 20% in Cordova, 26% in Malakai Tribe, and 30% in Molokai, which is in Hawaii. And we can significantly increase the clean energy generation by 919 megawatt per year in Cordova, Alaska, using the preferred technology. And whereas in case of Molokai, Hawaii, we can generate around 3 megawatt of electricity per year if we implementing the solar PV over there. That's all. Thank you so much. Yeah. Yeah.
What's community reception towards offshore hydrokinetic projects, especially in Cordova, which is a community largely dependent on fishing?
Yeah. So our the goal of this main project is to identify which technology is best suitable for that particular technology or for that particular region, because we have to consider the multiple factors, right? The factors like what is the energy potential for that, all of these 12 technologies for that particular region. So you cannot consider the solar PV over to that location. You have to look for the solar potential over there as well, right? So that's why we have considered all these 12 technologies, look for the community's needs, look for also for the energy potential over there. So by defining all of these different parameters, that's how we come to a conclusion that the marine hydrokinetics are going to be the best suitable for that particular technology, because you have to consider about how much is the potential for the tidal energy over there or the wave energy over there. So that's how we have defined everything over. Yes, yes. Yeah, so we take a feedback from all of these from these communities to get to know about what they basically wants, right? So because the problem is, again, it's been pretty far from the mainland of US, right? You don't have that skill labels over there. But yeah, you have to consider all of these minor factors, and you have to be defined well in the framework. That's how it works, because you cannot consider a single objective to be 100%. Suppose if you consider the marine hydro, if you want to give the suppose 100% value to a single technology, but this framework is not going to work in that way. Actually, it give you that it's not going to fulfill all the demands of the communities. Yeah.
It sounds like you've really considered everything about these communities for making that transition.
It's a it's a not a kind of the communities are backing off. It's a kind of US government is still looking for whether it's a good option to go with this particular technology, because it's a kind of, you can say, approximate results, right? You cannot rely on it's being 100% sure. But yeah, we are still working on it to actually with the government as well as with the community, so that we can close that gap between both the government and these communities, so that we can try to implement that technology in a particular region. Thank you. Yeah.
And when you do the analysis, there's probably a significant gap between the cost of the solution you'd say looking for, like, I'm drawing this maybe your hydro solution.
Yeah.
Did you get any feedback?
Yes. So because there are some of the studies being carried out to these remote communities from pretty long. So some of these community, for example, in Molokai, there are a lot of studies been done by the other lab since 2002. But when you try to implement that same technology in that particular remote communities, it fails. So that's why you need to go over there and look for all the parameters why it fails. So that's what we are right now trying to do, because we need to go over there and look for all the energy potentials for each of these technologies over there, so that we cannot fail when we have to implement that same technology in the remote areas. So that's what we are right now doing in collaboration with DOE. Thank you. For the presentation, and this is a